and welcome to Cisco Live. Today's session is on ASR 1000 OTV deployment modes, and we'll touch a bit in depth on one of such modes, which is OTV appliance on a stick. A short intro of myself. I am Uma Mohanty. I work for technical services in Cisco from past 3.5 years. So before we move in to the agenda or topic itself, this is what OTV on stick is. I have OTV and I have it on a long stick. What I'll do is just magically spin this, and both of your data centers can now extend the VLANs over the stick itself. So let's start off with the agenda for today. We'll start off with the dub of OTV. That means the what and why of OTV. We'll discuss in depth a bit on all of the architectural aspects of OTV. Then move on and see the role of ASR 1000 in the world of OTV. The next topic is the important one, which is OTV on stick. We'll touch a bit in depth or look at the packet walk, how exactly OTV on stick is deployed in the network. Then top it up with few health check commands. The next segment is an interesting one, which is packet tracer. And believe me, any tech engineer who has worked on OTV issues, it's really a rescuer. Then we'll look a bit on the configuration part. What configurations do we need to use in order to make OTV on a stick to work? Then sum it up with a few key takeaways from this particular session. And I'll open the room for any particular questions. So, start off with OTV. It's Overlay Transport Virtualization. This particular technology fits into the DCI, or Data Center Interconnect technology. And these are the three main points which OTV will guarantee or would try and achieve. Any workload in that matter. Any workload means it could be any kind of applications. OTV will be able to provide you the services over it. Be it any kind of clustering technologies, be it any kind of high availability protocols, OTV will be able to provide you the services over that. Anytime and anywhere in that matter means OTV is basically agnostic to the underlying transport layer itself. Be it IP, be it MPLS, any kind of transport layer you have, OTV will be able to provide you the services over that. So the session will probably focus on mostly the architectural aspects and deployment benefits of OTV. And we'll learn in depth how exactly to deploy OTV on stick with ASR 1K. All of the ASR 1K families, starting from 1001 till the 1013s. By the end of this session, I really hope that we have a better understanding of the data plane and the control plane, how they work together, providing you a VLAN extension on a unicast mode. We'll touch a bit on the multicast mode itself also. What this doesn't include the session is some of the path optimization technologies and some of the workload mobility applications or specific deployment considerations to that. But we already have some of the sessions which specifically talk about these particular technologies, and it's freely available on Cisco Live portal. I believe everyone has access to it. So you can just go through them if you want an in-depth analogy on the path optimization technologies or workload mobility. Probably we can sit after the session. If you want some pointers to it, I can guide you with that. So let's have a look at the distributed data center goals. What does this mean, distributed data center? My data centers could be distributed all across the globe. Probably some of my servers sitting in US users or the applications, probably the users who are using these applications sitting somewhere in Australia, something like that. And these are the 4 key points which we'll try to achieve, or which are the goals of a distributed data center. My business should always run. The second thing, distributed applications, as I said previously, the applications could be used in Australia, and there could be a difference in the geographical locations. Yes, there will be a bit of latency, but OTV will ensure you that it will be able to provide you the services. Seamless workload mobility. That means, let's say at some point of time, one of the users who was in data center A has just moved on to data center B, or in that matter, not exactly a user or a virtual machine in that matter. OTV will ensure that it will provide you the same services which you are using in data center A on data center B also, without any kind of interruption to it or any kind of config change. Maximize the computer resources. This particular point I would like to stress on. Think of the disaster recovery site. What does it do?
It'll just sit silent, waiting for the primary site to go down at some point of time. If it goes down, it'll take over and provide you the services. But why keep it idle? OTV can ensure that it can push some of the applications towards that idle CPU. It's kind of a load balancing. We are maximizing the resources of our data center.
जब हम खाना खिलाने गए तो पता लगा कि एक बच्चा कई दिन से खाना नहीं खाया था। उसका माँ बीमार थी, उसका पिताजी नहीं थे। चेहरा ऐसा लगता है।
Let's have a look at some of the current data center solutions. EO-MPLS. It's a bump in the wire and would require MPLS to work on. VPLS in that matter is something like between the data centers. It's a layer 2, or it's a switch which will provide you all the layer 2 MPLS services. But in VPLS, how the full mesh network is achieved is via pseudo wires. All of your data centers would require a full mesh connectivity
via the pseudo wires. I have a picture in the upcoming slide, and that is probably how the VPLS pseudo wires would look like. If you think of it physically, that is what it will look like. And believe me, it's a pain for the network administrator to troubleshoot on the VPLS issues when he goes ahead to add some of the pseudo wires, to remove some of them, or to troubleshoot some of the pseudo wires which has just gone down. Let's see what are the challenges that these layer 2 VPNs have, basically. The flooding behavior. We would never want our data centers to be flooded with unwanted traffic. OTV will ensure that the flooding behavior is stopped, is restricted. The pseudo-wire maintenance with a full mesh network, and this is the picture which I was talking about, and that is how your pseudo-wires would look like if you think of it physically. It'll be a very hard task for a network administrator in that matter to go ahead and troubleshoot on them, to add some of the pseudo-wires, to remove some of them. For n number of sites, you'd require n cross n minus 1 by 2 number of pseudo wires for a full mesh connectivity.
And that's a huge amount if we talk about some 4 or 5 data centers, if you go ahead and connect more than that. OTV will try and go away of these pseudo wire maintenance and build a dynamic tunnel itself based on who are the interested neighbors. And last but not the least, the multi-homing feature. If we look into today's world, if we think about the 6500s, we have some of the multi-homing technologies over there, something like VSS, something like stacking, multi-chassis ether channel. What we do, take 2 switches, put some configuration onto it, bundle them in, and they will be acting as one and will be providing you a multi-homing service. But the configs are pretty intensive. We just want to automate that with OTV. We'll see how exactly we are achieving these 3 major challenges of layer 2 VPN. Dynamic encapsulation is one such feature which will allow you to go away from the pseudo wire maintenance itself. What it does is basically the control plane will try and build a negotiation between the neighbors, and some of the tunnels will be built on top of it to the interested neighbors itself. And since we are making it more dynamic, due to this encapsulation feature, since we are making it more dynamic, we are going away from the pseudo-wire maintenance. Optimal multicast replication. We would never like a hidden device going ahead
and preparing different copies for or replicating the traffic itself and sending it to its neighbor. If I think it from a WAN perspective, it's quite inefficient because it'll eat up your bandwidth. With OTV, what we'll ensure via this dynamic encapsulation feature is that we will try and not the head end doing the replication, but basically the multicast core itself doing the replication for you and sending the traffic towards the interested neighbors or inside the group itself. Multi-point connectivity and point-to-cloud model in that matter. It's something like if I want to talk, I could use two of the scenarios. One is broadcast and the other one could be multicast. Broadcast, in that matter, if I go ahead and broadcast it, yes, you will be able to get it, but some of the uninterested parties who don't want to listen, they will also get those traffic. We want to go out of it. We want to send it via dynamic encapsulation. We want to make sure that it goes to a set or a subset of users or a subset of neighbors itself. Now, when I talk about encapsulation, that is not enough. Probably we could have gone for GRE. What does it do? It encapsulates the IP packets and sends it further. We just don't want to know whom exactly to send the traffic, but with this particular feature, protocol learning, what we ensure is we know whom to send the traffic and we know exactly where that particular host is located. What we achieve via it is we preserve the failure boundary at the edge devices itself. Since it becomes like before even sending the traffic, the tables are built properly and it will ensure that the traffic goes to the correct destination. The built-in loop prevention mechanism, OTV will ensure that it restricts the BPDUs at the edge device itself. And this particular feature is built in. You don't need any kind of configurations to activate it or let's say to make it work. You don't need to trigger it. It is all automated in OTV. When I talk about automated multi-homing, same thing. It will ensure that this particular multi-homing can be achieved without a single line of config. Site independence in that matter. Let's talk about VPLS. It's a large STP domain. One single packet can create a loop and a disaster in your network, right? What OTV does is it restricts the BPDUs or the STP traffic within the edge device itself, and all of the data center in that matter will do the same. So the site is quite independent. You can think of it as, okay, if I'm the edge device itself, you can think of it, I can tell the LAN devices, okay, I'm responsible to take some of the traffic of yours, some of the traffic from you and send it towards the other data centers. But I will have the authority all the time. I would know what traffic to send ahead. If there is a need, I can go ahead and drop some of the traffic. That is how OTV maintains the site independence itself. OTV on ASR 1K, the support started with XC35, and this is where the multicast mode started. And the unicast mode probably started with XC39 release. Let's have a comparison between some of the L2VPN features and OTV. I've highlighted a few points over there, not taking you through the whole of the table, just a few points, few important points. Multi-homing. In EOMPLS, in L2TP v3, the multi-homing, there's no multi-homing at all. With VPLS, we can achieve that, but we have to add additional protocol, BGP. What OTV does, multi-homing is built in. Again, loop prevention. The loop prevention mechanism for these, for MPLS and and the L2TP v3, it's point to point. But when I talk about VPLS, it's one large STP domain. In OTV again, it's built-in feature. Manageability, when it comes for a network administrator to manage the OTV services which are being provided,
When you talk about these layer 2 VPNs, they are pretty config intensive and probably need some other protocols. Like in VPLS, we use many kind of protocols on top of VPLS. But in OTV, we would need a single protocol, and very minimal amount of config is probably required. When I talk about single protocol, there'd be a question coming in your mind at the moment that, okay, are we going to use any such protocol to make OTV work? No. It will be running in the background itself, and you don't need to configure that specifically. Let's have a look at some of the terminologies which OTV has. Edge device. Edge device is the one which will perform all the OTV functionality. This is the device which will at least have one such interface towards the outside world. Then, talking about the internal interface. The internal interface is a plain regular L2 interface, and there is no OTV configuration required on the internal interface itself. This is the interface which will carry your VLANs that needs to be extended over the OTV towards the other data centers. Join interface. Join interface is the uplink of the edge device. I told you one such interface would be there in the edge device which will be facing towards the outside world. That is the join interface. It's a plain L3 interface, and probably 2 data centers having one join interface each should be able to talk. The transport layer should be maintained. The routing should be good enough so that OTV can be built on top of these join interface. Now, there are a few restrictions to the join interface. It can only be a physical interface, sub-interface, or a port channel. You might think that, okay, I can make a service instance, I can create a BDI and build a OTV on top of that. It doesn't work. It has a restriction that BDIs won't work as join interface. Overlay interface. Now, one more question might arise over here is like, okay, OTV, everyone knows that it's a layer 2 extension over the layer 3, right? Now, as I told you, the join interface itself is a L3. Now, what about the overlay interface? That's the one which will do all kinds of encapsulations, all kinds of decapsulations when it gets the packet from the other data centers and extend the VLAN over towards the data centers. This overlay interface will have all the OTV configurations, and it will ensure that all the VLAN traffic is extended over it towards the data center. Whatever it learns from the internal VLANs, whatever MAC addresses it learns from the VLANs, it will ensure that I propagate that information to all my neighbors, be it a multicast mode, be it a unicast mode. Let's see how exactly the control plane of OTV is built. The control plane learning is with proactive MAC advertisement. And as I told you, there is a single protocol which is running in the background to propagate these MAC address informations. That is ISIS. We are not reinventing anything over here, but just leveraging the ISIS protocol to do the job for us. ISIS protocol has an ISO standard TLV which can propagate the MAC addresses itself, and that is what we are leveraging on. We'll learn the MAC addresses from the LAN devices via flood and learn mechanism, probably, yes, and then via ISIS, which is running in the background, it will propagate it towards the other data centers. Do we need any kind of specific configuration for ISIS? No. It's all inbuilt. Now, with this, it also prevents unknown flooding. If there is any unknown unicast flooding, if it doesn't find it in its control plane, OTV edge device will make sure that packet is dropped and not propagated towards the other data centers. When we talk about the unicast flooding sections, which is in the upcoming slides, I'll probably explain to you in detail, and some of the other platforms which support it also. Now, before even the MAC address is advertised or we exchange some information, we need to do a neighbor discovery, right? Why would I try to talk to someone who is not even interested to talk back to me? We need to build a neighborship. This neighborship is built via the unicast mode or a multicast mode. Two modes of operations, and that is how the neighbors discover each other.